Okay, so this is lesson 18. Again, a lot of people were absent for lesson 18, so I'm going to do another video just to kind of catch you up. And this is the beginning of support vector machines and a lot of the math that's involved in it. So this is just geometric, a review of MA205 if you had that, or 255 if you were in that one. But vector calculus, that kind of stuff, that's really all we're doing with this first lesson, and maybe a little bit of nomenclature. So start off with a little bit of nomenclature because we might have changed it up a little bit. But let's let X be the matrix of all of our predictor variables, starting with x11, x12, all the way to x1p. Again, we have p predictor variables. This x11, the first one, stands for the row, obviously. I mean, because it's a matrix here, but that's the data point. So this would be one data point, x11, x12, all the predictors for that first data point, x21, 22, 23, all the way to 2p would be the, and so on and so forth, right? So that's the idea behind it. And what we're going to do is we're going to let y be the classification. In this case, for support vector machines, we're going to let y, and it's just going to help us out when we get to the optimization piece. We're going to let y1 and or y either be a -1 or 1. So it's a little different than we've done in the past. We'll let this be y be the class, and we'll let this be a -1 because it's down here. It doesn't have to be. I mean, we could turn this around if we wanted to, but this could be. We're going to let this be class and it equal to +1. So that's what your x and y's are, predicted variables, and sort of the classification that goes along with them. And then I just want to make sure that you get, when we use this, when I get the ith one of these x's that comes out of this matrix, that's the ith row. So let that be a row of x, capital X, right? So one of these rows, and it's equal to x11, x12, dot, 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 x1p. So that's one set of data for that particular row that corresponds to the classification that's on y1. So this row obviously goes with that y1 and x2. So I'm sorry, this would be x1 would equal this. And if I wanted x2, it'd be the second row and it would correspond to y2. So just making sure that that's clear when we get that over here and start talking about how to describe, or how we're breaking up the space. And really that's all support vector machines are, or how we're going to break up the space. So you can see some data points here. So these are separable data. And what we want to do is get a line that separates this data as best as possible. So in this case, let's see, W transpose X. Yeah, I'm going to come back and we're going to explain these here in a few minutes. I meant to erase these and write them in later. Right now, these might not make sense to you, but you'll see that there is so y equals mx plus. There's a way to describe a line or a plane or a hyperplane, depending on what space you're in. There's a way to describe it like this, and it looks the same way every single time. And so that's the notation that we're going to. But let's explain that notation real quick. So if we're in R2, y equals mx plus b hopefully makes sense to you. We want to convert this to be w1 x1 plus w2 x2 plus b is equal to 0. So if I was going to do that, if I just want to take some random, and we'll do an example down here, but we could take negative, just using algebra, and take a negative b on this side, and we could easily convert this to, and then instead of using x, use x1, instead of using y, use x2, and then let b be b, basically, so negative b on this case. We could do this fairly simple, and here's an example. Y equals negative x plus 2. That turns into x1 plus x2 minus 2 is equal to 0. So very, very straightforward. And just by taking this on the other side, you get the 1x1, and then the 1 is the 1x1, the 1x2, and then -2 on the other side. So if I were to graph this line and this line, they would be exactly the same. In R3, it's even easier because if you remember the equation from Stewart, I think everyone took Stewart as a calculus text. ax plus by plus cz is equal to d was the equation, and we can simply just turn this into ax1. So again, x1 being x, x2 being y, x3 being z, and then had -d. So that's fairly straightforward. So let's just see what this looks like in R2. That we want, why we want to write it this way, I guess, is really so wx plus b is equal to 0. And if we let W equal to, let's see, what was this one? Oh, this one right here, 1, 1. So W was 1, 1. And X is obviously just X1, X2. And B is equal to, it's not a vector, it's a scalar, -2. Then we can simply write this as W transpose being 1, 1, X being X1, that's not a vector, X1, X2, or I can put -2 here, is equal to 0. So this, I'm claiming that this is exactly the same as writing 1x1 and all that. So, and you can see if you just did this multiplication, it would be to x1 plus x2 minus 2 equals 0, which is what we had up here. So again, just check that out. And if I were to go to R3 now, well, how would this be different? Well, I claim that this is exactly the same. The only thing that changes are our W. So let's let W, again, I'm going to arbitrarily just 2, 3, 4, because I have so much creativity. And then X is just going to be X1 through X3. And if B is just going to be some number, we'll let it be -5, we'll let it be +5 this time, +5. And then if I were to write W, so again, W transpose X plus B, and now we're in R3 is equal to 0, then it just be, it's the same exact format, except for my W is now 2, 3, 4, X1, X2, X3, and then +5, oops, +5 is equal to 0. So again, rewrite that. It's just 2x1 plus 3x2 plus 4x3 is equal to -5. All right, so again, this thing doesn't change regardless of what dimension we're in. We're in R3, we're in R2, and so that's the goodness, right? Y equals mx plus b would be hard to change that into something that we could use in R3, as you can see. Okay, and then if this is the case, then if it's equal to 0, then what I've done here is I've created this set of data. So I got the class, all of the data that's with this x1 and x2 coordinate, right? So its predictor variables are down here, and it's red because it has y values of -1. And these all have their x1 and x2 values up here, and there are blue because they are class +1, right? So I got -1 and +1. And so now what I want to do is I want to create this thing called a maximal separating classifier. And what is that? Well, that's this line right here. So I'm going to take this line and I'm going to put an arbitrary point into it. Like say maybe we're trying to classify that point right there. And when we put that point in, if we put it into this equation and it's greater than 0, then we classify it as a 1. If it's less than 0, then we classify it as a red. So obviously, if this were my line and these were all 1s, then this would be some number greater than 0. So it would classify correctly. And the ones that get close to the line are the ones that you really have to worry about, right? So this thing right here is called the margin. Oops. This is called that part and that part. This is the margin. When you're talking about support vector machines, we're trying to make this margin as large as possible. And how do we make this margin as large as possible? Well, what I do is I pick the closest blue or the closest class 1 point, and then I make that line that goes through there. It's parallel to my maximal separating classifier. I make that parallel line equal to 1, and I make the one that goes through the red point that's the closest to the blue -1. And by doing that, we're going to find out here in a few minutes of how to make this equal to 1 and that one -1, and then find that the biggest the W's that make this thing the largest. So that's the idea for this particular lesson. In order to understand that, in order to do that, we need a couple of things. And the first one is we need to remember scalar projections. So I think this is a pretty straightforward thing, but I don't know, maybe it's not. So let's remember what we're trying to do. So scalar projection so what we're projecting is this vector A onto B. And the question that you're answering is how much is A pointing in the direction of B? So so what is this distance here, right? So you can kind of see it. I've already written it in. The only thing you have to remember to understand this or to remember how to do this is this fun fact here, right? So I'm not going to rederive this. Go back to your MA205 if you want to check it out. Stewart does it. I think it's just a triangle identity that does this. But I mean, we got to start somewhere. So we're going to start remembering, or say that everybody remembers that the dot product between two vectors is the magnitude of the one, magnitude of the other times the cosine of the angle in between them, which is exactly what our setup here. So if this were the case, then I would say that the length of this vector is a, and so the magnitude of a is the hypotenuse of this triangle that we got written here, right? So this is a right triangle. You know, if it's right on that side, obviously it's right on this side. And then using simple trig, what can we do? So using simple trig, we note this. We note that the cosine of theta is equal to the adjacent, which is distance. That's the thing we're trying to find, divided by the magnitude of a. And what does that do? Well, I know I can just use simple algebra now. Say distance is equal to, right? So bring the magnitude of a over. So the magnitude of a times the cosine of theta, right? And so that's the answer, right? So we could do this every single time. The problem is if I give you two vectors, well, I don't really know what theta is unless I do use this formula up here. So I want to make this a little bit simpler in order to do that. So how do I make it simpler? Well, what I want to do is I want to try to make it look like this equation so that I can change that out for the dot product. So that means I'm going to multiply this piece here by the magnitude of b, because if I do that, then I know that's just a dot b. Well, the problem with that is if I multiply magnitude of b, well, then I also have to divide it by the magnitude of b. Why? Because this just means I'm multiplying by 1, and this quantity doesn't change. And if that's the case, then we get something that looks like this: the magnitude of a, magnitude of b times the cosine of theta over O. And the other thing is, if we're doing distance, then we got to make sure that it's the absolute value, especially when you bring the cosine in. It's the absolute value over magnitude of b. I don't have to worry about the denominator because the magnitude of b will always be positive. And then we know that it's a dot b over magnitude of b. So that's where the formula comes from. It's not that difficult. And if you look in the book, I think it calls it the component. And this is what I'll do here in a few minutes: the component of a in the direction of b. So we'll use this formula here a lot in the next couple minutes. Actually, I'm going to stop this video and I'm going to have a separate video starting for the next piece, right? So just so you know, I'm gonna do this first, and then all this introduction stuff and a couple of these derivations, and we'll actually this is enough. We'll stop the video here, and I'll come back and I'll give you a second part to this where I use the scalar projection and I use everything in order to find the distance from a point to the plane and the distance between two planes. And so that's the idea for the rest of this piece. All right, so in order to make this video a little bit shorter, I will stop it here and I will start another one here in a few minutes.